Hi, my name is Salasi Dumeno, and my partner is Andres Cordova, and this is our presentation 6 for ENGI 460, and today we're going to be talking about simulation and finance. Alright, so a quick overview here. We're going to be looking at the Brownian motion. We're going to look at asset price movements, and then the bulk of this presentation is going to be dealing with pricing, simple derivatives, and options. And under that, we're going to be looking at the European call, the European put, continuous income, and then delta hedging. Alright, so the Brownian motion is basically a stochastic process, and by stochastic here we mean, it's randomly determined process, and we're going to say for W subscript T, initializing that T is greater than or equal to 0, so it can be a non-negative real number. And then we're going to define it on a common probability space with the following properties. So W subscript 0 is equal to 0, and then with the probability of 1, the function T basically maps onto WT. It is continuous in T. Another property will be that the process W subscript T has stationary independent increments, and then the increments WT plus S minus WS has the normal O, T distribution. And here the term independent increment means that for every choice of non-negative real numbers, let's say from 0 less than or equal to S1 less than T1 less than or equal to S2 less than T2, so basically all the way to infinity. And then the increment of random variables as well will be WT1 minus WS1, and then comma WT2 minus WS2, and then for the number of random variables, so for let's say 23, it'll be WT23 minus WS23, so N represents the number of random variables, and then we say that they are jointly independent. Okay, so next we're going to talk about asset price movements. And let's say, suppose we wish to model the price movements over time of an asset, such as a share, interest rate, or a commodity. If X of T represents the price at time T, then the most frequently used model in finance is the dx over x is equal to mu dt plus sigma dB, where sigma in this case is greater than or equal to 0. So it cannot be a negative, and basically a negative number. And then one thing to take note of is that the left-hand side of that equation represents a proportional change in the price in the interval, which is basically T, comma, TDT. And this process can be very useful in determining the realizations of how prices of assets can change over time. So next we're going to move on to pricing, simple derivatives, and options. And we're going to be looking at the European call first, then we'll look at European put, continuous income, and then delta hedging. Alright, so European call. This option can be exercised at the end of its life, at its end, or at the end of its maturity. European call, which has a known exercise T and price K, and also the price of an asset at time T. The terminal condition in this case will be V of X of T, comma T, which is basically equal to X of T minus K. The solution of the equation is subject to the boundary condition, which turns out to be the equation below, which is V of Xt, comma T is equal to the exponent of negative R, T minus T, times the integral X minus K, fxr of T bar, Xt is equal to lowercase xt of X, comma, X times T dx. And this is from negative infinity to infinity. Now, one thing to take note of that very confusing and complex equation is the fxr T bar, X of T, is the density of the asset, price X at the expiration time, given that the current price is known to be X of T. And taking the expected growth rate to be R, and the risk-free interest rate. Right, so the European put, just like the European call, can only be exercised at the time of its maturity. And then, let's say, if we're trying to put this in a scenario, and then we let P of t denote the price of the option at time lowercase t, the value at time uppercase T will be the max, which will be basically x of t comma k. Therefore, the values of these two portfolios at time lowercase t must be equal. Otherwise, arbitrage would be possible. And that follows the equation C of t plus k exponent negative r times uppercase t minus lowercase t should be equal to P of t plus x of t. And this result is usually known as put-call parity. And when we want to deal with continuous income, we can basically we can modify results when the underlying asset earns continuous known income at a rate R of f. And the equation for that is d pi will be equal to the partial v of partial t dt plus 1/2 of partial squared v over d over partial x squared sigma squared x squared dt minus partial v partial x of x rf dt. And when you simplify that, what you get is r times v minus x partial v partial x dt. And the corresponding Black-Scholes condition for this would be that basically partial v partial t plus 1/2 partial squared v over partial x squared sigma squared x squared is equal to rv minus r minus rf times x partial v partial x. And then finally we come to delta hedging, and this option aims to reduce the risk of associated price movements in underlying assets by offsetting long and short periods. So it's a strategy that is based on change in premium caused by changing the price of the underlying security. There's not really much to say about this, but it's basically useful when you want to minimize risk, and it also tells you a lot about your position and portfolios.